Okay, let's resume our afternoon section. Our second speaker today is Huy Fan from Stanford University. He's also the winner of Frontier of Science Award. And he's going to talk about what are structures robust under random sparsification.
Thank you. Yeah. So again, I would like to thank the International Congress of Basic Science for organizing this wonderful event. And so in this talk, we'll investigate this fairly general question: when are structures robust under random sparsification? So let's start with a stylized but not far from realistic scenario. So let's say that you have a large set of clothing items. Among these clothing items, you have only certain bundles or combinations of items that you are interested in. So let's say these are the combinations of clothing items that you can wear to the ICBS conference 2024. And unfortunately, you left home for a while and your dog has randomly chewed on your clothing items. So now each of the clothing item in the collection is wearable or uncorrupted with probability P independent of each other. So in particular, each single clothing item is corrupted with probability 1 minus P. So this is like an example of the scenario. We have our clothing items. The gray lines signify the bundles of items that we are interested in. And the items that are corrupted are removed from this picture. So these are the remaining clothing items. In this talk, we'll be interested in the regime where the probability P is fairly small. So the corruption probability is fairly large. And in this scenario, you may ask the following question: when or for what value of P or under what kind of condition can you still likely find at least one bundle that entirely consists of uncorrupted items so that you can wear it? Okay. Now, let's say in real life, we are not necessarily immediately unhappy as soon as one item from the bundle is corrupted. So let me introduce also the following scenario. So we have the same setup, and let's say that we were just unlucky enough that there is no entire bundle of items that is uncorrupted. Well, in this case, in a bundle of items, even though some of the items may have been corrupted, you may still be happy as long as these items are not very important in this bundle of items. So to model that, let me say that in each bundle of items, you have assigned to each item in the bundle a certain non-negative value, and let's normalize so that each bundle has a total value of 1. In this talk, later on, you will see that we will work with very general valuations. We don't make a lot of restrictions on the valuation. And I just want to say that this is a fairly natural assumption to work with. So for example, let's note that an item may have different values in different bundles. So for example, a red hat may have a higher value in a bundle of items that are all red compared to its value in another bundle of items that have multiple colors. And in this case, if we have an incomplete bundle of items, let's assign to it the value that is simply the sum of the values of the uncorrupted items in this bundle. Okay, so now we want to be happy. So the question that we ask is, what can we say about the typical best, or in particular highest value bundle that we can find after the random corruption has been applied? So both of these questions are instances of the following questions. We are asking, when are our bundles of items robust to random corruption? And more generally, we will soon see, we are asking the question, when are certain structures of interest to us robust to random sparsification? And as we have seen, there are multiple notions of robustness that we just saw. The first is the more restrictive notion, where we want an entire bundle to remain uncorrupted. And the second notion, we want a slightly weaker notion where we only want a bundle that is mostly uncorrupted. And this notion of most is in terms of this valuation. So before getting to the formal mathematical details, let me just go through some of the basic and intuitive obstructions. So what are the kind of conditions that would tell us immediately that our bundles of items cannot be robust to the random corruption? And the first obstruction is very simple. You may have been just too selective. If you have a very small number of bundles of items that you are interested in, then as long as the corruption probability is not very small, it will be highly likely that all of your small number of bundles of interest will be severely corrupted in the random corruption. Okay, so we'll see later on slightly more precisely that the reason here can roughly be phrased that the expected or the average number of uncorrupted bundles after the corruption is applied will be too small. And there is a slightly more complex but still very intuitive obstruction. So in this case, let's say you have this scenario where you argue that you have a large number of bundles that you are interested in, but there's a single item that you are very interested in. So this black shoe, you demand that all of the bundle of items pass through this black shoe. Again, as soon as the corruption probability is high, then there will be a high chance that this black shoe is corrupted. And as soon as it is corrupted, all of the large number of bundles that you are interested in would immediately be severely corrupted. So in this case, you can say that even though you are interested in a large number of bundles of items, they all cluster on a very small, brittle set of items that is prone to the corruption. Okay, so far I introduced this in a very stylized scenario, but this general question of asking when a structure is robust to random sparsification, it is a central and it's extensively studied theme in various parts of probability, combinatorics, and theoretical computer science. In particular, this general question encapsulates important central questions in random graph theory, and you will see throughout the talk later that motivations from random graph theory will be a very important source of motivation and insights for us. So with that, let me go to introduce the formal mathematical details of the discussion that we just had. So first, I will focus on the first notion of robustness. Let me call it robustness for containment. This is when you want an entire bundle of uncorrupted items, and this is closely related to the formal notion of thresholds, which I will introduce next. So in this formal setup, we have a finite set X. Think about X as your set of clothing items. We have a collection script H of subsets of X. So think about these as the structures that you are interested in, the desired structures, or in other words, they are just the bundles of clothing items that we saw before. Now, we'll define XP to be a random subset of X, where each element of X remains in the set XP independently with probability P. So this XP is exactly just the set of items that are not corrupted. And let me introduce now one notation. Let me denote bracket H, the collection of subsets W of X that contains at least one of the structures from the collection of desired structures script H. So the question that we phrased informally before can now be phrased as follows. We are asking, when does XP likely contain some structure from the collection script H? Or in other words, when is XP in bracket H with probability at least 1/2? Now, if you look at this quantity, so if you look at the probability that the random sparsification XP contains one of the structures from H as a function of the sparsification parameter P, then except for some very trivial degenerate situations, this function will evolve continuously and increasingly from 0 when P is equal to 0 to 1 when P is equal to 1. So there will always be a unique point that we see here as PC of H, where this probability is exactly equal to 1/2. So you can think about this point as the point where we transition from unlikely containing a structure from H to likely containing a structure from H. So we'll define that to be the threshold of the family of structures script H, and we'll denote that PC of H. Okay, so now our question that we were interested in before can be roughly phrased as the question of determining the location of the threshold PC of H for a given family of structures script H. Okay, so now let me say that this is a general setup that encapsulates a lot of special cases that are of interest to us. So the first case is the case of the Edish-Rényi random graph GNP. This has been introduced in many of the combinatorics talks already. And Edish-Rényi random graph GNP is simply a graph or a network on n vertices where each pair of vertices is connected independently with probability P. So to see that it is a special case of the general setup, you can take X to be the collection of all pairs of vertices on n vertices, and then XP would correspond exactly to the Edish-Rényi random graph GNP. And in the context of Edish-Rényi random graph, this is the type of question that we usually want to ask. So given a certain graph H on n vertices, when does the random graph GNP likely contain H as a subgraph? So in particular, this question is a specific instantiation of the general setup where you simply take the collection script H to be the collection of all isomorphic copies of the graph H on n vertices. Okay. You can, of course, consider Edish-Rényi random hypergraph as well. So this is what you would obtain if you start, instead of letting X be the collection of pairs of vertices, you can let X be the collection of R tuples of vertices among N vertices, and then XP would correspond to what we would call an Edish-Renyi random hypergraph. Now, you can also think about an Edish-Renyi random graph as what you would have by starting from the complete graph on N vertices and then removing the edges independently with probability 1 minus P. We don't have to always start from the complete graph. So starting from a general graph G, you can define a random subgraph, let's call it GP, where each edge in G is retained independently with probability P. I'll call this doing edge percolation, starting on a general graph G. And again, we can ask the same kind of question. So if we have H, which is a subgraph of G, when does this random subgraph GP still contain H as a subgraph? And let me state here, here's another specific instantiation of this type of questions. We can take G to be some fairly explicit structure graph, like a d-dimensional box. And let's say that the center of the box is 0. And we can ask, when does GP likely contain a path from the center 0 to the boundary of the box? This is, again, some certain special instantiation of the general setup that we are looking at. And this is a question that is of very much interest in the study of percolation in probability theory. So there are a lot more cases, a lot more models of random graphs and other random discrete systems that will fit into this general question that we are studying. So for example, random Cayley graphs, random lattice square graphs, and so on. But let me not go into further details here. Instead, I will return to the intuitive and simple obstructions that we saw before and put them on formal terms. So let me define one notation here. So let me denote NH of W, the number of structures from the collection script H that is contained in the set of elements W. Now, the first simple obstruction that we saw, let me call it the naive expectation obstruction, that will simply correspond to what you would obtain by doing a naive union bound, where you upper bound the probability that XP contains at least one structure from the collection script H by the expected value of NH of XP. Okay, so now by linearity of expectation, you can explicitly evaluate the expected value of NH of XP, and it will be this expression on the right-hand side on the slide. So in particular, whenever you can explicitly evaluate and see that this expression on the right is small, is less than 1/2, you also conclude that the probability that XP contains one structure from H have to be less than 1/2. If you look back at the definition, all that is saying is that P has to be a lower bound to the threshold PC of H. Okay. Now, we had one slightly more involved notion of obstruction before, so let me call that the expectation obstruction. This is when H doesn't itself have the naive expectation obstruction, but it sits on top of a naive expectation obstruction. So formally, let me say that a collection of subsets of X, H prime, is a cover for H if any set from H contains entirely some set from H prime. So in the figure, you see that the cover H prime is a small purple set, and they sit underneath the set, the larger set from the original collection script H. So now, just a trivial observation, whenever we have a cover H prime for the family of structures H, then if we have a set that contains at least one structure from H, it must also contain some structure from H prime. So you have this simple upper bound. You can upper bound the probability that XP is in bracket H by the probability that XP is in bracket H prime. And now we apply the naive expectation obstruction to the family H prime. So we get the inequality here. So we chain all of that together. What that means is that whenever this quantity on the right-hand side, so the expected value of NH prime of XP is small, smaller than 1/2, then we also have that the probability that XP is in bracket H have to be smaller than 1/2, which again means that P is a lower bound to the threshold PC of H. So let me say that a family of structures H is P small if there exists a cover H prime of H for which the same quantity that we saw on the last slide, so expected value of NH prime of XP, and let me now just abbreviate it as the cost of the cover H prime under the parameter P, is smaller than 1/2. Okay, so from our discussion so far, whenever H is P small, then we know that P is a lower bound to the threshold PC of H. And so the expectation threshold will simply define it to be the best lower bound that we can obtain by using only these very simple naive expectation obstructions. And so in particular, the expectation threshold, which I will denote P of H, is the largest P for which H is P small, but let me flip it and say that it is the smallest P for which H is not P small, for a reason that will be clear later. And from all that we discussed so far, the expectation threshold is a rather naive lower bound to the true threshold PC of H. So one important question, which we will return to later, is whether this lower bound that comes from only these very simple obstructions can come close to being tight in a general situation. But before going there, let me go through some examples just so that we have some more feelings for these obstructions in action. So I cannot resist from going back to the beginning of time to, again, this one of the very first results in probabilistic combinatorics, this remarkable theorem of Edish that also, I guess, appeared in Jack's talk just earlier. So Edish proved that there exist graphs on a large n number of vertices with no clique or independent sets of size 2 log n. So based on your last talk, you know that this is an application to Ramsey's theory. This gives a lower bound, an exponential lower bound on the diagonal Ramsey's number, but that is not where I'm going into. Instead, I just want to remark that Edish theorem has a remarkably simple proof. All that we need to do is to consider the random graph Gn1/2 and the collection of structures script H, which is the set of cliques or independent sets of this specific size, 2 log n. And we can explicitly evaluate the expected value of NH of Gn1/2, and with some simple calculation, we see that this expected value is too small. So in particular, there is an expectation obstruction, in fact, a naive expectation obstruction, forcing most graphs on n vertices to have no clique or independent set of this specific size. Okay, so our discussion, in some sense, go back to this very beginning of probabilistic combinatorics. Now let's see some more examples. The next example, we consider the setting of the random graph GNP, and the collection of structures H that we consider will be the collection of all cliques on 4 vertices among n vertices. Again, the expectation is very easy to evaluate. It's around n to the 4, p to the 6. So in particular, this family H is going to be C n to the negative 2/3 small for some appropriate small constant C, let's say 1 over 10. And in particular, you get a lower bound on the threshold of containing a K4 that is of order n to the negative 2/3. In the next example, let's consider just a slightly more complicated situation. So in this case, we have the collection H is the collection of all K4s together with the pendant H. So it looks like this. Again, the expected value is very easy to compute. It's around n to the 5, p to the 7. And the naive expectation obstruction would tell us that this family of structures H is going to be C n to the negative 5 over 7 small for some appropriate small constant C. But in fact, because both of these examples are sitting on the same slide, we know that we can do better. These K4s together with the pendant H, they sit on top of the K4s that we see in example 1. So in particular, the family of structures H in example 2, they are also going to be C n to the negative 2/3 small. Okay. Now, in both of these examples, they are small bounded size graphs, so they are kind of easier to handle. And in fact, we know that the lower bound on the threshold that we just obtained from the expectation threshold are actually quite close to being tight. So in particular, in both cases, if you take P to be very large compared to n to the negative 2/3, then GNP will indeed contain the required structure, either a K4 or a K4 with dependent H with high probability. And now this is an instance of the second moment method, which shows that in this regime of parameter, this random variable NH of GNP is going to concentrate. Okay, so before continuing, let me just go to the last example, which is going to be just a little bit more complicated. In this case, the structures that we are looking for is the family of perfect matchings. So now we consider n to be an even number, and a perfect matching is simply a collection of n over 2h that covers each of the n vertices exactly once. Okay, so now it is different from the previous examples because in particular, the family of structures that we are looking at, their size grow as the number of vertices n grows. Okay, again, the expected value of nh is fairly easy to compute in this case, and in particular, this family of structures is going to be C over n small. And in fact, let me not tell you why now, but the expectation threshold, so the best lower bound that you can obtain from the expectation of structures will indeed be of order 1 over n. But unlike the previous two cases, even if P is very large compared to 1 over n, you may still not contain any perfect matching typically. So in particular, if P is even some small constant times log n over n, which is asymptotically larger than 1 over n, because of isolated vertices, it will still be the case that G and P doesn't contain any perfect matching with high probability. But indeed, if you change the small constant c to a big constant, so if you are looking at a random graph with density c log n over n, then there will now indeed be a copy of H of the perfect matching with high probability. So in this case already, we see that it is now fairly different from the previous two examples. And in fact, the random variable nh is quite a lot more complicated. We won't be able to just naively use the second moment method, even in this regime that p is a large constant log n over n, to prove that the random graph contains a perfect matching with high probability. In this case, it won't be so hard. We can use Hall's matching criterion, for example, in order to show this result. But we already see that here we need to use some fairly specialized property of the family of structures that we are looking at in order to derive when there is a copy of the structure with high probability. Okay, so let me summarize what we just discovered. We saw that the expectation threshold just tries to capture the simple obstructions to the containment of structures under random specification. And then in the examples, we saw that it can be much harder to obtain the guarantee in the complementary regime. So this is the regime where you have no obstruction, and you want to show that in the case that there is no obstruction, there has to be structures that emerge. And we saw that this may be especially challenging if you are looking for a large spanning structure. And so the question that we want to understand is this one. Is there a good sufficient condition to guarantee robustness of structures under random specification? And well, even in the 2000s, this question is kind of the important underlying questions behind a number of important long-standing open conjectures at the time. And so partly motivated by that, Kahn and Kalai pose a very bold and beautiful conjecture, but a conjecture that up to a small change, in fact, having no expectation of obstruction is both a necessary and essentially a sufficient condition in a precise sense that I will tell you about later. And in the context of that time, because, well, based on this conjecture, all of the long-standing conjecture in probabilistic combinatorics, which are really instances of this question for specific nice symmetric family of structures, would immediately follow from this conjecture. Well, they thought that this may be too strong to be true in general, that this general principle may more likely be false than true. Now, over the years, many of the motivating conjectures for the Kahn-Kalai conjecture are indeed resolved positively in very beautiful groundbreaking works in probabilistic combinatorics. But in each case, it requires a challenging and highly ingenious argument that is specially adapted to the family of structures that we are looking at. So it's still not clear from there that there would be such a general principle holding true. So with that, let me now introduce to you the formal statement of the Kahn-Kalai conjecture. So we saw before that the expectation threshold PE is always a trivial lower bound to the threshold PC, and Kahn and Kalai conjecture that they are actually always fairly close to each other. So the true threshold is in fact always upper bounded by a constant times the expectation threshold times a factor of log x. So think about this log x as kind of a small logarithmic factor. More precisely, you can phrase this as follows. Whenever the family of structures H is not P-small, so think about being not P-small as kind of a nice combinatorial condition, that is a condition that stands for robustness. We'll see it repeatedly. Then if you look at the random specification of X, where the parameter is now C times P times log X, then this random subset will likely contain some structure H from this family script H. And likely means with probability at least 1/2. So in earlier work with Jin-Young Park, we resolved the Kahn-Kalai conjecture in general. In particular, we show the following slightly more precise statement. We show that if we have a family of structures H that is not P-small, and let's assume that the maximum size of a set from H is at most the parameter L. So you can always take L to be the size of the universe X. Then if you look at the specification of X with probability Cp log L, then it will contain some structure from H with high probability. So in particular, this is saying that the threshold is lower bounded by the expectation again. This is the easy direction, and it's upper bounded by a constant times the expectation threshold times log L. Okay, so just maybe some interpretation. You can just think more intuitively that the statement is saying that up to a small change, up to a logarithmic factor, in existence of expectation obstructions are essentially both necessary and sufficient for containment of structures after random specification. Now, to me, the Kahn-Kalai conjecture is also a very beautiful conceptual statement. It is telling us that, again, up to this small logarithmic factor, the first moment method is a very simple method that we first see in probabilistic combinatorics, is in fact the fundamental driving force, so that it dictates the much more complex threshold phenomenon. Okay, now let me remark that the weaker fractional version of the Kahn-Kalai conjecture was originally posed by Talagrand, and that is closely related to the main lemma behind the beautiful sunflower breakthrough of Alweiss, Lovett, Wu, and Zhang, and then by introducing an additional twist on the sunflower argument that was later sharpened by Frankston, Kahn, Nayanan, and Park. Okay, so with that, let me just say a little bit about, okay, why can the Kahn-Kalai conjecture be useful? So it turns out that for a lot of the applications that we were interested in before, so in particular, thresholds are really hard to get a direct handle on. So before we only consider questions that for which the structures H are nice symmetric families of structures. And in these cases, it turns out that the expectation thresholds can often be easy to estimate. So in particular, Kahn-Kalai conjecture would imply immediate corollaries, a few seminal results in probabilistic combinatorics, for example, the beautiful result of Johansson, Kahn, and Wu on the threshold for containment of a R-uniform hypergraph perfect matching was Shamir's problem from the 80s, and a result that was proved earlier by Montgomery using the absorption method for the threshold of containment of a fixed bounded degree spanning tree. Although let me say that the absorption method does give a stronger universal guarantee than just a guarantee for a single bounded degree spanning tree. Okay, but with that, let me actually now turn to the second notion of robustness that I promised at the beginning of the talk, and we'll see that we'll travel to a fairly interesting different landscape in this discussion. Okay, so let me call this notion robustness for almost containment. Okay, so let me introduce the formal setup for this notion of robustness. Again, we have the same kind of object. We have the same general finite set X, same family of structure script H, and we'll look at, again, the specification XP, a random subset of X. In this case, for the notion of almost containment, we will introduce the valuation. So for each of the structure from H, we introduce the valuation lambda H. This will simply assign to each element from H a certain non-negative value. Okay. Now, if we have a set W of items, we'll define the value of W under the valuation lambda H simply to be the sum of the valuation under lambda H of all of the items that are contained in both W and H. Okay. And again, we make a simplifying normalizing assumption that the total value of each of these valuation lambda H is equal to 1. Okay, so the question that we wanted to ask at the beginning of the talk was, well, what is the typical value of the best or the highest value bundle, which is more precisely this quantity here. So we want to maximize over all of the structures in the collection script H of the valuation under lambda H of a random subset XP. Okay. Okay, so now let me give a few remarks before going into further details. So first, because of our normalizing assumption, whenever XP contains entirely some structure from H, this maximum is going to be equal to exactly 1. So in fact, for this kind of question, we are slightly more interested in the regime where the parameter P is below the threshold PC of H. So it's still somewhat hard for us to contain entirely some structure from H when we take a random specification. Second, let's note that if I drop this maximization, if I look at a single term, lambda H of XP, then its order will be typically of order around P. And we want to think about P as a parameter that is arbitrarily small, extremely small. So in particular, each single term, lambda H of XP, you want to think of as being very small, typically. Now, instead, we want to be working in a regime where something interesting happens. So one regime that is of interest to us is when, even though each single term is small, when you look at all of the terms collectively, when you look at this maximization, then this max, the highest value bundle, can actually be guaranteed to be a lot better than a typical one. So in particular, we want to guarantee that this max is at least some absolute constant that is independent of the arbitrarily small parameter P. Okay, so with that, let me now go into the story. So it turns out that this story will connect to a very interesting, insightful picture by Michel Talagrand, and it is in fact motivated by the study of suprema of random processes. which is one of the important topics where Talagrand left a very deep impact on. And Talagrand was just earlier awarded the Abel Prize for this and the many other contributions that he made in probability theory. Now, to say like how this picture is connected to the obstructions or the notion of p-smallness that we discussed before, let me slightly rephrase the Kahn-Kalai conjecture in the following form, and we'll see kind of a new role that the expectation obstructions can make. Okay, so one way that you can phrase the Kahn-Kalai conjecture is as follows. So if you look below the threshold, in fact, if you look slightly below the threshold, specifically a logarithmic factor below the threshold. Now, since you are below the threshold, you know that the probability that xp contains one of the desired structure has to be small. Particularly, it has to be smaller than 1/2, since you're below the threshold. Well, the Kahn-Kalai conjecture can be said this way. It's saying that if you look, well, a log factor below the threshold, you don't only know that the probability of containment is small. In fact, you can certify or witness the smallness in the probability by using these very simple expectation obstructions, or by, in other words, by using the naive union bound over very kind of simple explicit events. Okay? So in fact, this kind of general recipe of trying to quantify the structure of events, of tail events or events with small probability by saying that they can be explicitly certified by simple structured events is the underlying theme of a number of other conjectures of Talagrand in a number of different setups. So in particular, Talagrand made very beautiful conjectures on similar phenomena in high-dimensional convex geometry in the 90s, and then in a study of suprema of random processes. The one that we will discuss today is what we refer to as the selector process conjecture. And roughly it says, we'll come to the precise statement quite a bit later, that tail events of suprema of certain positive random processes can be captured or witnessed by simple structured events. Okay, and it turns out that this statement, which is just about certain stochastic processes, is intimately related to the combinatorial discussion that we have so far. So it turns out that the Talagrand selector process conjecture is very closely related to the notion of robustness of almost containment under arbitrary evaluation, which is the notion that we are looking for. Okay, so with that, let me tell you what is precisely Talagrand selector process conjecture. And in fact, instead of stating the original version, let me just go with this version that is more familiar in our story so far. Okay, so he conjectures that if we have a family of structures H that is not p-small, again, condition for robustness, then for any choice of the valuations lambda H, we will have that the best value bundle, so the maximum of lambda H of xp, maximized over H, will typically be at least of some absolute constant order. Note that this absolute constant is completely independent of the parameter p. Okay, in other words, so in earlier work with Jin Young Park, we proved that Talagrand selector process conjecture holds. And you can think about what it is saying. It's saying that the inexistence of expectation obstructions, now at the same density, you don't need to go up by a log factor anymore. It implies this notion of robustness, of almost containment under arbitrary evaluation. Okay, so if this is a little bit hard to parse, let me just state one corollary that is one very simple special case of this theorem. And that's the case where your valuation is particularly simple. You just assign uniform weights across all of the elements of H. And let's even assume that all of the structures H have the same size L. In this case, what the theorem is saying is that if you optimize over the structures in H, then a random subset xp will intersect at least one of the structures in H in at least a constant fraction of that structure. Well, again, note that if you drop the supremization, then this will be just typically of order p times L. Okay, so you see that, well, this corollary is not very far removed from what we want for the Kahn-Kalai conjecture. So the first notion of robustness, if you imagine somehow that you can strengthen this statement and iterate this, or each p sample of a random subset of X is able to capture a constant fraction of the structures from H. So in logarithmically many iterations, you can hope to capture entirely some structure from H. That is not exactly how the proof is written, of course, but it is actually not a bad intuition for how the proof of the Kahn-Kalai conjecture goes. Yes. Yeah, I understand that. So, right. So of course we need some condition here, but the point is just that no matter what the size of X is, and no matter how P depends on the size of X, as long as you satisfy this combinatorial condition of being not p-small, then no matter how you assign the valuation, the typical order of this best value bundle is going to be some absolute constant. And in fact, you can trade off various things to improve the constant to be close to 1, so on and so forth. But yeah, kind of maybe the surprising point is that this very combinatorial condition of being not p-small, condition about the support of this valuation is sufficient to allow you to obtain this kind of conclusion. Yeah. So yeah, maybe just again a mini side story. You can kind of think about what you want for proving the Kahn-Kalai conjecture as working in the setup where these valuations lambda h assigns uniform weights to the elements in H. And in fact, more precisely, something like that is true. Whereas for Talagrand's conjecture, we have to work in this very challenging general setup where the valuations can be pretty much arbitrary. But it is very important that by forcing ourselves to work in this general challenging setup of Talagrand's conjecture that we were crucially motivated to discover the key notion behind the proof of the Kahn-Kalai conjecture, that is the minimum fragment. So it's somewhat interesting that we were guided by really this kind of more rougher environment to find out about the right idea. Okay, so there are actually a lot of other interpretations of Talagrand selector process conjecture. For time reason, I will not really tell you about them. There is an interpretation about a kind of function that is of interest in theoretical computer science and market design. And there is the last statement is something that is related to, again, a very curious phenomena behind one of Talagrand's conjecture, but let me not go over these details. Instead, let me finally tell you about the original version of the selector process conjecture. So I told you it came from the study of suprema of stochastic processes. In particular, well, the understanding of Gaussian processes, suprema of Gaussian processes, is essentially nearly complete, and this is largely thanks to many mathematicians, Fernick and others, but crucially also Talagrand in settling the celebrated measurizing measures theorem. And going beyond the Gaussian case is one of the outstanding challenge in this area. And Talagrand again makes a beautiful web of conjectures that would take us closer to achieving this goal of understanding suprema of general processes. Now, some of the pieces in this beautiful web of conjectures have been studied, have been resolved in the last decade. And a crucial missing last piece is the understanding of suprema of general, so the crucial missing last piece in the understanding of general processes turns out to be the understanding of certain positive stochastic processes called positive selector processes. This is one of the Talagrand's unfulfilled dreams in this area. And so now I want to introduce you what are these selector processes, and they are in fact very familiar to us based on the discussion that we have so far. Okay, they are pretty much just what we just saw when we discussed the notion of robustness for almost containment. So in this setup, we have a collection big lambda of weight vectors lambda. So each of the weight vectors will assign a non-negative weight to the elements in our universe X. Now, given a weight vector lambda from the collection, and given a subset W of X, we can define the selector process indexed by lambda and driven by the set W, so Z lambda of W, simply as the sum of the valuation lambda at the elements in W. Okay, and now what we are interested in is going to be the suprema. So Z of big lambda, which is when you maximize over all weight vectors lambda in the collection of the selector process Z lambda driven by a random sparsified set XP. Okay, and now in the language of these processes, we can state Talagrand selector process conjecture as saying that if you look at the tail event of the suprema of the selector process, so if you look at the event that the suprema exceeds its expectation by some universal constant, then this tail event, well, it's a tail event, so its probability is going to be small, but it will not just be an arbitrary event with a small probability. In fact, it will be p-small, so it's kind of small in a very structured way. Okay, so again, an instance of certifying the smallness of a rare event by explicit structured event. And in fact, there is another class of stochastic processes generalizing the selector processes. So general positive empirical processes, and Talagrand is a related question there, which we also resolve in our work. Okay, so with that, let me actually go to this question as a small apology. So in the entire talk, whenever I mention expectation obstruction or p-smallness, I added an adjective, either naive or simple. But, well, are they really simple? Do we actually have a way to get our hands on these supposedly simple expectation obstructions? or they are indeed simple in a conceptual sense, but it doesn't mean that they are easy to work with. So, well, if you want to, for example, determine the threshold of some family of structures, and if you want to use something like the Kahn-Kalai conjecture, then an important task is to estimate the expectation threshold. Okay? Now, by definition, lower bounding the expectation threshold is going to be easy. All that you need to do is to establish some cover, explicitly evaluate its cost, and check that its cost is small, so that the cover is p small. Now, upper bounding the expectation threshold is slightly more non-trivial, but there is at least for all of the for the simple applications that we so far consider, there is a fairly general robust method, and this is an argument that is explicitly written down by Talagrand. Roughly, you just go through the fractional relaxation and apply linear programming duality, but at the end of this process, what it means is that you can upper bound the expectation threshold as long as you can exhibit a certain probability measure supported on your structures that has a certain nice property that we usually call the p-spread property. It's not so important for now what this property is, but it turns out that, like, fortunate for us, in all of the applications that we consider so far, because the threshold is very hard to determine, we consider fairly simple families of examples, and in all of these examples, the structures are sufficiently simple and the setting is sufficiently symmetric that we have very easy ways to get our hands on a matching lower and upper bound to the expectation threshold. So in fact, all of these cases, roughly all that we need to do is to do some trivial enumerations. Well, but now that we have this general tool, we may want to go beyond the simple kind of applications. You may want to generalize just a bit beyond them to go to some more complicated models or to look for some slightly more complex structures. And immediately, we find that we are in trouble. When we don't have these enumerations, it immediately becomes not so clear how we can achieve this task of upper and lower bounding the expectation threshold. So this is roughly where we are. We have the threshold, which we want to get to, and we have spent a lot of time trying to build this bridge between the threshold and the expectation threshold. But we are standing ashore, and it's just, in general, it's not clear that we have a robust way to arrive at the expectation threshold so that we can go to the threshold. So I will not say much about this. Let me just say that in the recent years, there have been a flurry of work, so a lot of exciting developments along this task of roughly estimating the expectation threshold. When this trivial, easy enumeration is not available, there have been a lot of progress, and they bring about a lot of interesting connections to other areas. And yeah, there are some of my works, but there are also works of other people in the audience. And I won't say too much about the details here, but let me just say that what is involved, at least in some of my works here, is some algorithmic view on the problem, and what we end up employing the ideas and tools from a variety of areas. So from the previous cornerstones in extremal combinatorics, like regularity method, embedding lemmas, the absorption technique, as well as some ideas that we borrow from theoretical computer science, like the Lovász-Larkó lemma and their algorithmic aspects. Okay, so so let me end here, and I'll just say that there would be, I think that it's an exciting place. There would be a lot more to discover, both on the side of the conceptual phenomena and on the side of better understanding the expectation threshold and where it connects to, be it combinatorics, additive combinatorics, or other areas that we can find insight in. Okay, thank you.
Okay, thanks for your wonderful talk. Now, questions? Is there any questions? Maybe I have a very naive question. I remember that there's a inequality which looks like PE larger than PC and less than some constant some value, right?
So yeah, so P.
Yeah, and I wonder whether whether the inequality on the right part is always non-trivial, or when it is non-trivial, because it can be something larger than one. I remember it is a product
So
of the
the
three
inequality
terms.
is PC is at least PE. PE is always at most PC.
Yes, and there's another one.
Oh yeah. So
Yes, that one always. Can we find a non-trivial bound? Because that is something like three terms product of three terms and it may be larger than one, and actually it's just a trivial balance.
Yeah, so we already saw actually in one of the examples, in the example of the perfect matching, we saw that the expectation threshold is of order 1 over n, and the true threshold is of order log n over n. So yeah, so actually the upper bound PC at most PE times the log factor times an absolute constant, that is generally tight. So we would need the log factor there. And in fact, for most of the examples involving spanning structures, the log factors would appear there. So in general, we cannot improve the inequality unless we have special assumptions on the family of structures that we are looking at.
Okay.
So maybe this is a very naive question because I'm not from this area at all, but I mean, in many cases, there are thresholds in combinatorics are sharp. You haven't talked at all about this. Does that happen here?
Yeah, so, well, in fact, for many of there are kind of two separate phenomena here. There's a phenomenon of how sharp the threshold transitions around its correct location, around PC, and that was more or less better understood based on your Boolean function analysis developments back in the 90s. And so for a lot of the properties where we don't know where the location of the threshold is, we actually already know that we would have a sharp threshold, a small window. Yeah, but yeah, so it turns out that determining the location, there are some connections, and there were previous pathway, for example, to the Kahn-Kalai conjecture going through developments on sharp thresholds, but it turns out that they seem to be fairly separate. Yeah.
Any other questions? Maybe another question by myself. For about the Kahn-Kalai conjecture, so can I rephrase it like this? There is a critical value PC such that if P is larger than PC, then there is a Kahn-Kalai conjecture, which is when it is not P small. When P less than PC, then it is something. It is actually the case of P small, so we don't have this conjecture.
Yeah. So okay. So maybe we clarify the question. So yeah, if our family H is P small, then yeah, there's nothing we can do. We know that the probability of containment of the correct structure is going to be small. It's less than 1/2. And what we were saying here is, well, if it is not P small, then not so far away from P, it is going to be at least 1/2. And
so the Kahn-Kalai conjecture is actually based on this PC, right?
it is about the PC, about the threshold.
So it is universal for all most of the problem that this.
Yeah, so it is completely general. It applies to any kind of structures that you want to place on a discrete set.
Okay, thanks.
Yeah, actually.
So just to continue my previous question, so the Kahn-Kalai conjecture gives you a bound with a some logarithmic freedom between the upper and lower bound. So how does that compare to the width of the threshold? I mean.
Right. So yes. Okay. So well, so far what we know explicitly is that there's this lower bound, this upper bound. Both sides can be attained in general. Let me actually comment also a little bit on the previous question. There are cases where, for example, we can explicitly find what should be exactly the expectation threshold, and in these cases, we just maybe somewhat related to sharpness of threshold. We also expect the threshold to be exactly there, so it saturates the left-hand side of the inequality. But in general, when, for example, second moment method and similar things don't work, we actually don't have a very good handle on determining which exact location in this window of logarithmic length the true threshold should be exactly at. And yeah, and I think that there should be some fairly interesting phenomena that underline where the final threshold would be. And there are cases where the threshold would not come at the log factor, would not be matching the expectation threshold, but perhaps there's some fractional power of the log factor. And it would be related to something interesting. For example, I think it would be related to the structure of the best cover that we can find at an appropriate parameter. So yeah, so it's a lot more to be discovered, and I think that is one of the kind of driving questions that would lead to more interesting phenomena. Yeah, so far we have a very short proof of the Kahn-Kalai conjecture, but the virtue of being short, it is fairly rigid in that if you inject some additional assumption, if you change things a little bit, it is not easy to see how one can use that to remove the log factor in general.
Can this approach be applied to a more general case like the random to random number?
random two-run number,
Yes.
which
That is in a random graph. You give the how many edges can you have? Can there is with hyper probability there's an edge in G.
yeah, so yeah, there's a right. So there's a large family of questions like random two-run, random Ramsey type of questions, and well, yeah, so far they seem to be challenging. And well, one of the reasons that they are challenging is that for these type of property already, the expectation threshold would get fairly complicated, and that's where we don't get a handle on. So yeah, so for example, resilience type of property seems to be well still so far quite hard to arrive at. Yeah.
Any more questions?
Is there any relation between the thinking about the Kahn-Kalai conjecture and the Talagrand's conjecture?
Yeah, so yeah, so they are certainly related. I guess I just kind of said that in a very informal way in the talk, but so they are both about kind of robustness. They are both about trying to capture certain structures, and so certainly in that sense they are related. And yeah, so that was like how we arrived at the proof of Kahn-Kalai conjecture is in fact by working on Talagrand's conjecture, and it's about capturing structures in a slightly more dynamic and more complicated environment. But it turns out that in that environment you would need more ideas. Plus, kind of it somehow feels that you are required to use what is on this picture, but I didn't explain at all, which is the minimum fragment. And just extracting the minimum fragment, you can arrive at the proof of the Kahn-Kalai conjecture. Yeah, but I don't know if that's a very good explanation of how they are related to each other, but yeah, they are related, in the end, related to each other in a very interesting way.
Thank you for your excellent talk. And I have a question, maybe technical, about the proof of the Kahn-Kalai conjecture. In the proof, the key point is to construct a cover and to iterate to reduce the size of the set X. So which step is crucial for the log n, for the gap of log n?
For the what?
For the gap of log n. In fact,
for the factor log.
PC is less than PC times PE times log n.
Yes, so roughly, I mean, so roughly in the proof, there was a corollary here, and there is something that is very similar to the corollary stated here, but it's in a strengthened version that would be the key step in the proof. So the key step in the proof is to kind of reduce the size of the structure that we have to capture by some constant factor by using one additional random subset of X of density P. So if once you can prove that, then you can iterate, and the size of the structures that we need to capture would just decrease exponentially, so they would decrease to 0 in logarithmically many steps. Yeah, so the key lemma is a certain variant of this corollary that I'm not stating here, but it's very closely related, very closely looking to this corollary on the slide. Yeah, so that's why there is a log factor, because there's a constant here. So yeah, you get 1 minus c to the number of times that you iterate.
Maybe we can stop here. Let's thank our speaker again.